Today we're going to cover circular motion. So circular motion, of course, is motion that moves in a circle. Should make sense. There's a bunch of pictures on this slide showing you different types of circular motion. We could have the merry-go-rounds, like a parks, a laundry machine moves in a circle, a car turning moves in a circle, even if it doesn't take the whole circle, if it moves in part of a circle. And so we still have a area of constant radius. It's still circular motion. It doesn't have to make a full circle to still be circular motion. It just has to follow the path of a circle. And it's going to have some specific properties that we're going to talk about. But before we can do that, we need to just review circles. It's been a while. Make sure we know all these things. We know that first, the circumference. Circumference is the distance around the circle. And it is, the equations are 2 pi r or pi times d, where r is our radius. Our radius is our distance from the center to the outside of the circle. And our diameter is the distance all the way across the circle, otherwise also, which is also 2r. So we should know that. Our diameter is equal to 2 times r. And know that if we have some sort of circle, we can take like angles of the circle, right? And we need to remember that the angle all the way around the circle is 360. One full lap is 360 degrees. Okay. So something you may not have seen before is something called arc length. I don't know what your teachers have taught you in the past, but there's a formula called arc length. And arc length is the distance of a particular length of the circle. Okay, so you can see this picture here. If I have some sort of angle of the circle, right? Some sort of angle theta, I can find the arc length. I can find this section of the circle right here that takes up that angle. It could be any angle. I could also have a really small angle right here. We can call this theta. In which case, our S is just the arc length, just the length of the outside of that section of the circle. And we need to be able to find the length of that because given a problem, a car may only make, a 70-degree turn, right? 70-degree turn, which means that they're only turning from here to there. But I need to know how much that is. I need to know how far that car travels so I can figure out the velocity and so on, right? And so we have a formula. The distance d, which in this case is our distance, this is our arc length, is equal to pi times r, so pi times the radius of the circle, all times theta over 180 degrees. So whatever your angle is in degrees, divide it by 180, and then multiply by pi r. If you Google this formula for circle arc length, you're going to get different variations of this. They're all congruent. A lot of them, though, assume you know how to use radians. If you know how to use radians, you're going to have an edge on this course. Great for you. I'm not going to require that you know how to use radians yet because not everybody's in pre-cal. Not everybody has had some experience with it yet. And so we're only going to be using degrees as an angle in here. And so that's why we use this formula here, because this transfers, this is going to basically convert from what we would, there's a formula, the default formula is in radians. This formula makes it so that our default angle is in degrees. So how do we use this? Well, let's say we have a railroad track that turns 80 degrees and has radius 70 meters. What is the distance traveled by the train along this path? And so what's going on is we have some sort of angle of 80 degrees, so almost a 90-degree angle. And so the track follows that path. The path curves in a circle like this, and it goes 80 degrees, and the radius of the circle is 70 meters. And I want to know, how far does that train actually travel? The train starts here and goes here. How far does the train actually move? Okay. And so we just plug into the formula. D is equal to pi our theta over 180. And so we're equal to pi times our radius, which is 70 meters, times, what's our angle? 80 degrees divided by 180 degrees. And so I'm going to do 80 times, I'm going to do the degree part first, 80 divided by 180. And then I'm going to multiply it by 70. And then I'm going to multiply by pi. And we're going to get an answer, 97.7, and we can round there, meters. And that's how far we travel. Easy enough. You should be able to go between all of them, though. So you should be able, make sure you practice this. We're going to have a worksheet today that goes on it. We're going to be able to go solve for anything. So if I give you the distance in r, you should be able to find theta and so on. Tangential velocity. So this is the term that talks about the velocity of an object at any particular moment. So if we have an object traveling in a circle, at this moment, forget about the circle. At this moment in time, we have a car, right? Let's say this is a car. Okay. At that particular moment, if you stopped turning, if you just let the steering wheel go and it just went straight, we would be going this way, right? Our car would just keep going in that direction. It wouldn't keep turning. It would just go straight. It's only because we hold the steering wheel that we go in a circle. But Newton's first law says an object in motion will stay in motion unless there's a force. And so the tangent velocity is what we call the velocity at any particular moment. At this moment in time, this car is going this way. It's going along that velocity vector there. Whoops. Okay. The magnitude of the velocity is just the speed. So in this problem, we're only going to be moving in circles with constant speed. So all the cars are going to go around the circle at the same rate. Okay. The entire time. They're not going to speed up or slow down. But the velocity is changing, right? Why is the velocity changing and the speed not changing? Well, the velocity has to do with magnitude and direction. So the magnitude of the velocity is the speed, which is constant, right? And so the magnitude of the velocity is constant. The reason that the velocity changes is that we are changing our direction. As we move in the circle, our velocity vector is changing. It's going different directions. And we call all these points in time, we call all these vectors at these points the tangential velocity. And really when we refer to the tangent, we're really talking about the direction. If you ever heard the word tangent before in math, it means it touches the circle in one direction. So we could draw a tangent line to this point like this, because it touches the circle at one point. And that's really what the tangent velocity is. It's the velocity that goes along the tangent line. We also have acceleration in this unit, centripetal acceleration. And this is really the cause of everything. Centripetal acceleration means sensor seeking. And so it turns out the acceleration, it's kind of funky. It's not super intuitive. The acceleration is, if we have a car like this, if we're moving this way, you might want to think that acceleration is this way in order to make the car turn, but that's not true. Let me just clear pen markings. There we go. The acceleration is as it's labeled here. It's straight down. The acceleration is always sensor seeking. It's always towards the sensor. So even though we have a constant speed, the velocity is changing. Therefore, we have to have some sort of direction. And the direction is always towards the center of the circle. Which means, based on Newton's, actually we'll get to there in a second. I forgot that we have an equation. So there's an equation for the acceleration. The centripetal acceleration is equal to v squared over r, where v is your velocity, but it's the magnitude of the velocity. So we really just write speed. We're really talking about speed here. and then r is your radius. And so if you do v squared over r, you get your acceleration, your centripetal acceleration. Okay. But based on Newton's second law, F equals ma. If we have acceleration, that means we have a net force. Therefore, we call the net force of centripetal acceleration the centripetal force. But don't get caught up in the idea that the centripetal force is a thing. The centripetal force is not a thing in itself. It's just describing whatever the force is that causes the object to turn. If I have a ball on a rope, okay, and I'm swinging it in a circle, the force that pulls it to the center is not, quote unquote, the centripetal force. What we're saying is that the centripetal force is tension. Tension is the force of the string pulling on the ball towards the center in order to get it to turn. Tension. And tension is our centripetal force. Okay? Centripetal force is not a thing in itself. It's a type. It's describing what the force is. Okay? And so don't get caught up in like, hey, we're looking for, like, I don't know what centripetal force is. It didn't tell me centripetal force in this problem. It's not ever going to really talk about centripetal force in a problem. It's going to talk about, oh, there's a tension force of this. Okay, well, that is your centripetal force. If you have a car on a road, it's actually friction that causes your car to turn. It's a frictional force that causes your car to go in a circle. Okay. And we'll get to some other problems. Sometimes we'll have a normal force that causes something to turn. Sometimes we'll have, we'll have a bunch of different types of forces. Sometimes it'll just be an applied force that causes an object to turn. Sometimes it's gravity, like for satellites, that cause the objects to turn in a circle and revolve around the Earth. All these forces end up being centripetal forces depending on the situation. And all of them, just like acceleration, because of Newton's second law, the acceleration is always in the same direction as the force. And so our centripetal force is also towards the center. Just like our centripetal acceleration. They're both towards the center. And there's an equation. It should be very similar. If AC equals v squared over r, then we can just multiply both sides by m, right? And not really change the equation. And then realize that m times a, well, that's just net force. So the equation's pretty simple. It shouldn't be too complicated. This is your A of C. And so all we're doing is multiplying m times a, but a happens to be an equation. And so we can put the equation in there and make it more easy for us. Okay. Let's do an example. A car of 500 kilograms turns to the right while traveling 22 meters per second. The radius of the car turns was 11 meters. What is the magnitude of the force of friction causing the car to turn? Okay. So I always like to first label my things. I have a mass. I have a velocity, a speed. I have the radius of our turn. And I want to know the magnitude of the frictional force. And that's causing the car to turn. And so it turns out our frictional force is our centripetal force. And so if we write down this equation for centripetal force, I'm going to replace centripetal force with frictional force, because frictional force is really what we're talking about here. We're looking for the frictional force, which is our centripetal force in this situation. And it's equal to 500 times, I don't know why it keeps doing that, 22 squared over 11. So I put in my calculator, 22 squared divided by 11 times 500 equal to 22,000 newtons. That is our centripetal force. Let's try another one. A 5 kilogram mass is on a string being spun in a circle. The length of the string is 2 meters and it is spun 8 times in 10 seconds. What is the tension force of the spring? Well, again, tension force is what's causing the object to move, so that is our centripetal force. our centripetal force equals tension. But let's write down what we know. We know our mass. We know the length of the string. And now we have an object on a string and it's moving in a circle. It turns out the length of the string is your radius, right? Object moves in a circle. It's on that string. That string is your radius. That string is telling you how far away from the center your object is moving. Our radius is 2 meters. And it's spun 8 times in 10 seconds. Okay. And so I'm going to write that down 8 times. And we have a total time of 10 seconds. And I want to know, what is the tension force? Well, this is a little trickier because we don't have velocity. And so how do we get it? Well, we have to use our definition from kinematics. Remember that average velocity is equal to just distance over time, or our speed really is distance over time. And whenever we're talking about velocity in this equation, we're really talking about our speed. It's our distance over time. Okay? Well, we have our time, so we just need our distance. Well, our distance is our arc length. Pi r theta over 180. Okay, well, we have r as 2 meters, but we don't have an angle. But we kind of do, actually. We know it's going to spin 8 times. 1 time is 360 degrees. So 8 times must be 8 times that. So 360 times 8 is 2,880 degrees. And so we plug it in, pi times 2 times 2880, all divided by 180. Plug it into the formula. And I got a distance of 100.53. And it says for our speed, we're dividing that by time. So 100.83 divided by 10. We get 10.053. And this is our velocity. This is what we're going to plug in here, because remember that in the equation, Fc equals mv squared over r. Our v is just really our speed because we're moving at a constant speed. And so we're just going to plug it in. Equals 5 times, I'm just going to round it to 10 because that is what we have here, divided by 2. And I got 250 newtons. With that, you should be able to complete the worksheet. It's not too bad. We're really just using this equation. Fc equals mv squared over r. We might be using this equation if we just want the acceleration. We don't want the force. We'll be using the arc length equation. D equals pi r theta over 180. And we'll be using speed / we can really just call it velocity because that's really the term we're going to use. Velocity is equal to distance over time. And so we can use all these equations and we're just puzzle solving. Write down your givens. Write down your goal. We're trying to get force, which means we need mass, r and v. Well, I don't have v. Well, I can get v from this equation. And well, I didn't have distance, but I can get distance from here. And so you're just kind of working backwards. Look for what you're looking for. See what you need to get it. And then step back, and just figure out how to get there. With that, you should be able to complete the worksheet. Have a good day.